We did this twice. And I think you could agree that the second time we did it, although it was more tedious, we are probably closer to the actual value than we were before. And let me just help with that. When I say closer to the actual value, you realize that we assumed the entire first 10 centimeters was concentrated in the point where the center of mass was. But there was clearly pieces of mass that were further away from the axis of rotation, which means that our estimate for that piece is probably a little lower than the actual moment of inertia. And that would have to be true for every piece, since for every piece, there's parts of it that are further away. Now, you could argue that there's also parts of it that are closer, but remember, distance is squared. So parts that are further away amplify the effect more than parts that are closer. So this is probably actually less than the moment of inertia of a meter stick. When we broke it up into 20 pieces, we probably got a little bit closer. A little bit closer. And clearly our number changed a little bit, but to two decimal places, they're the same number, right? 33. Actually, to three decimal places, they're the same number, right? 3,330. What I want to do today is I want to first reiterate a little bit about this, because I found out in third period there are people who don't understand what a summation is. I want to make sure that everybody's on the same page that understands what a summation is. But I also want to move us towards a more robust way to do this. You see, I need you to be able to calculate the actual moment of inertia of a continuous object in such a way that isn't an estimate, that is a more accurate depiction of its moment of inertia. But what I don't want to do is I don't want to break this up into every individual millimeter of a meter stick, because that kind of tedium is just beyond us. I don't want to do that. There is a method in place. Mathematics has provided a method that will allow us to do this. Before I launch into the method, though, first, for people who have never seen this notation before, I asked if there was anybody who didn't know what a summation was, and I had people in the room who didn't raise their hand, but I have come to find out that perhaps they just didn't feel like outing themselves as not knowing what this symbology is. Well, today we're going to be using even more archaic symbology. So if you are unwilling to admit that you don't know this, then you're going to have real trouble in a minute when I switch from that to this. So let's make sure we understand what this is telling us to do. Because although you were able to perform it, many of you were able to perform it, I should be able to give you any summation formula and you should be able to perform it. The letter I here is our incrementing variable. And I'm not trying to make that harder. It just means that it's our counter. It tells us which variable is going to change with each count. So I labeled M with a subscript of I and R with a subscript of I, because each individual point mass will require me to find out the mass of that point and how far away from the axis of rotation it is. So that's why there's an incrementer here. If there wasn't an incrementer on this one, it would just mean that I would be using the same value for each increment. I can't assume that's true for every case that we're going to see, but that's what this equation would say. It would say for every single one that you're going to use, M has to stay the same number. By putting the incrementer on there, I'm indicating that M will change with each object, or could change with each object. And R will change with each object. It's also telling me to start with object number 1. Makes perfect sense. And end with object number N. That's a placeholder that tells me, the person who's doing this, that I need to add it up for every single object that's rotating. That's all it's telling me. So for the meter stick example we just did, N was 10 in the first case, and N was 20 in the second case. That's how a summation works. Now, you guys who are a little bit more advanced in math, you know that there's some ways to play around with this, and you can come up with recursive formulas that will calculate the summation in a single calculation as opposed to actually adding up all 10 or all 20 numbers. Mathematics has provided some interesting ways to do that. And some of you probably know about that because you've done it before. Some of you probably haven't. You've probably never worked on trying to find a recursive formula that will do the summation. So has anybody done recursive formulas to try and find the answer to a summation? Usually most teachers kind of blow through it, but you might see it again towards the end of pre-calc. You might see it again in the middle of second semester Calc BC. I say might. I don't really know what the curriculum is anymore. They keep changing it. Now, this is known as the point mass formula for moment of inertia. And lots of things can be considered point masses. Basically, anything that is rotated with an axis outside of the object can be considered a point mass. A very likely example would be something like this. I give you 4 point masses. The problem might say they're connected maybe by some very thin, light bars that don't themselves have any real mass, or the mass is negligible. And so this is object 1, object 2, object 3, and object 4. And you might be asked to find, say, the moment of inertia if I spin it this way about an axis through object 4. That's not an unfair question. It's pretty typical. If that were the case, you could use the point mass formula with an understanding that you would have to find this distance, and this distance, and also an understanding that object 4 doesn't contribute to the moment of inertia because the distance to object 4 is 0. But I could just as easily ask, after I've done that problem, to rotate it about an axis that goes through these two. Well, suddenly it has a different moment of inertia. Object 1 and object 4 won't contribute to the moment of inertia, but object 2 and object 3 will probably contribute equally to the moment of inertia. This is a fairly standard point mass example. And you have this in your homework. Please make sure you've tried them. I'm not going to spend a lot of time on point mass problems, but be aware that point mass problems come up frequently. And one reason is because we do have example questions where we have composite masses, where we might have a bar with, say, a mass hung on the end, and we're going to rotate it, say, here. A composite object would require that we know the moment of inertia of the bar and a moment of inertia of the point mass. You see, moments of inertia, by definition, add together. I say by definition because our original definition is a summation. So clearly, if I have multiple objects, I add their moments of inertia together. It shouldn't change if our objects are maybe more complex. For something like this, you would probably have to know the moments of inertias of the basic shapes. And there's a chart in your textbook. Find that chart tonight. Look for it. It's just a chart with a bunch of shapes on it and the moments of inertia. It talks about a bar rotated about its end, and a bar rotated about its middle, and a sphere, and a disc, and all sorts of things, and a hoop, and a sheet. It has all sorts of moments of inertia. We're going to have to also do part 3 of this. So part 1 is point masses, part 2 are composite masses. Part 3 is you have to prove the moment of inertia of a continuously shaped object. That's the one that's challenging. That involves some math you've never done before. Well, or maybe you're just starting to do. But I want to tell you that whether you're in calculus or not in calculus, probably 80% of the process has nothing to do directly with calculus. So people who have had calculus only have maybe a 20% head start. That's still a head start, sure. But let me tell you, the hard part isn't the integral. That's actually the easy part. When you get to that part's going to be easy. The hard part is setting up the integral, something that's not really taught the way we need it in calculus. And if you don't have an appreciation for that, let me just kind of tell you that calculus is a tool like any other. I'm pretty sure that everybody in the room can tell me the answer here. I'm very hopeful that everybody in the room can tell me the answer here. And it's because you have a method. Either you add 6 together 3 times, or you add 3 together 6 times, or you have memorized the response. Either way, you have an answer, and you know how to deal with that answer. Going from here to here, that's calculus. That's the way calculus works, in that you have to set something up, and then you execute the derivative, or you execute the integral. The thing is, how did you know I was going to choose 3 and 6 here? Why did I assemble those particular numbers? Aside from this being an example, setting up the problem, that actually takes a certain amount of art. And that's what we're going to talk about today. How do we set up the calculation for a moment of inertia? And we're going to use an example to which we actually know the answer. I want to go back to the one we've just done. We're going to do a bar again. And we're going to rotate the bar about its end. And we know our answer's probably got 3's in it, right? We did this for the meter stick, and it was 3,330 centimeters squared per unit mass. I expect my answer to look like that when we're done. Now, I'm going to start this by throwing out something. There's actually so many little pieces here that I kind of expect you to know that I have found out in the past you don't. So to do this, I really need you to kind of do something else for just a minute. And it's not because I want to insult your intelligence, or because that doesn't mean that the meter stick isn't one-dimensional. It just means we're dealing with an object that's very long compared to its width or its thickness. So we can treat it as if it's one-dimensional. So I want to explain how we find the moment of inertia of something like this. It's likely I won't finish, but I want to give you the steps necessary to do this. First, we can't use the point mass formula. So although I've been talking about the point mass formula, and I'm going to put it up here, I'm putting it up here just so we have something to look at to compare it to the formula we're going to use. The formula we're going to use is still a summation, but it's going to assume that we have so many individual pieces that we can't just count them. This is the transition from algebra to calculus. And we're going to write it a little different, but it's still the same thing. The difference, of course, is the introduction of another letter, and I don't want you to get confused. The DM here is a package. They go together. It means a small piece of mass. Small piece of mass. I'm going to get a piece of mass. You understand that we say this enough times, one of you is going to mess up. I'm looking forward to that day with great anticipation. In fact, I can see it on the back of a t-shirt. All the piece of mass sayings that we could probably put together. Do you understand yet? Because I think it would make an excellent t-shirt. You'll have to say it out loud yourself to understand, and I'm not encouraging it. But one of these days, I'm going to ask you about the piece of mass. You're going to have to tell me if it's a good piece of mass or not, because you'll have to know if you want to use that piece of mass. Some pieces of mass work better than other pieces of mass. So in this case, the piece of mass I'm going to use is a small square piece of mass, somewhere out of the middle of my bar. And yes, I recorded that. 2.5 minutes of Mr. Shelton talking about it, the piece of mass on the paper. So yeah, there are still good times in school. So in the prior example, we chose a point mass and called it M. In this example, we're going to say it a little different. We're going to kind of carve out a piece of the object. And it's not dissimilar from saying delta M. The D here is just another form of delta. Delta means piece of. That's what it really means. So in this case, I'm not going to use the delta because I'm talking about a piece that is so small that the difference in the distance from one side of the object to the other side of the object isn't measurable. That's why we use a lowercase d here. So it indicates that this is a very, very, very small, thin piece of mass. Now, here's the thing that you have to do. And this is not obvious. We want to find a way to convert the part of this formula that's about mass and make it about length. This object has linear symmetry. So we want to try and make an expression for the mass that's in terms of the length and not the mass. And the reason might not be obvious, but it's because the rest of the problem is about somewhere on the bar. We would like all of the variables in this problem to be about location. Now, you don't have to understand why that's true, but you need to do it either way. So to understand what I want to do, you have to do two things. Thing number one, we have to figure out what the density of the object is. We need to use that like we used it before. So let's say that our object has a mass m and has a length L. Let's just give it some parameters that will probably be likely to be able to be used here. That would mean that the density of this object would be m over L. All right, so step one is done. I have something that I can reference as the density of the object. Okay? We good so far? I've given you step one. Now, step two is tough and will take practice. You need to pick a way of pointing to the piece of mass. I'm not going to make this super overly complicated. To point to the piece of mass, I'm going to assume that there is a starting point, 0, and that I can point to where my mass is with a straight line that is perpendicular to the axis. And I'm just going to call that x. The location of where the object is a distance x away. Yes, sir? You need to find a way to point to the mass that you've identified. Now, the method you choose to point to the mass has to be a method that will allow you to take in every possible piece. Meaning, is there a setting for x that gets the first piece? And is there a setting for x that gets the last piece? And will it be able to get every piece in between? This one's pretty easy, I hope. Right? If I set x to 0, then I'm referencing the piece that's right here. And if I set x to L, then I'm referencing the piece that's all the way at the end. And clearly, as long as x is somewhere between 0 and L, I can pick out every single piece on the object. Does that make sense? Now, that's because it's one-dimensional. It's pretty easy to point to every piece. If it was two-dimensional, I might have to work at it a little more. Now, this part's the part that will make you cringe a little bit, but you have to describe how big your piece is in terms of your pointer variable. Now, that's not as hard as it sounds. If I would like to describe how big my piece is in terms of my pointer variable, then I would say go out a distance x, and my piece is a little bit bigger, meaning my piece is a small distance in the x direction. That's how big the piece is. So I'm going to call that piece dx. It has a size, a length that is dx long. I'm using the variable that I'm pointing at it. I'm saying go out a distance x, and the piece that I'm pointing at is a little bit of x, meaning a little bit more in the x direction. Is that okay? Not terrible? Because here's the thing. If the density is the same everywhere, then dm over dx should be equal to m over L. It would have to be, wouldn't it? It's the same ratio everywhere in the bar, then the mass of that piece divided by the length of that piece should match the mass of the whole bar divided by the length of the whole bar. Is that okay so far? All right. So we have done two things. We have found a pointer that will work for our problem, and we have found a way to describe the mass in terms of the length. Just solve that for dm. All right. Done a lot here. Now we're going to assemble our integral. There are three parts to assembling our integral. First part, dm. We want to replace dm with something that describes the size of the object. That's what we did here. It's the mass of the object based on its geometry. So I will replace dm with m over L dx. Next, r squared. That represents the perpendicular distance from the axis to my piece of mass. I need to put the variable in there that will work to describe where that is. This one is super simple, right? The variable we're using is x. So I will replace r squared with the variable that describes where that piece of mass is. Again, if this were two-dimensional, this might be more complicated. But for a one-dimensional problem, it's pretty easy. The last thing we have to do is we have to set our limits. We have to tell the summation where our first piece is and where our last piece is. So our first piece is at 0. And our last piece is at L. That's the moment of inertia. You've done the hardest part of the moment of inertia. This is really the hardest part. The next part is like doing multiplication. It's executing the integral. That's a procedure. Now, I'm going to finish because I want to finish. I'm desperate for it. I have 2 minutes left. We've done this before. First, take a look at everything here. Anything that is not an x can be pulled outside the integral. So okay. This is now all that's left for my integral. And you've done this already this year. To do an integral, step 1 is find the antiderivative. This is a polynomial. Do you remember how to do the polynomial rule? So I'm going to take this. I'm going to add 1 to the exponent, and I will divide by the new exponent. That's the antiderivative. I haven't applied my limits yet. That's the next step. My next step is to apply my limits. That means plugging L in first, where x is, and then subtracting when I plug in 0 in for x. Good so far? Can we see that this will be 1/3 ml squared? One-third. 0.3 repeating, right? If you put 100 centimeters in for the length here, don't you get 3, 3, 3, 3? All right, guys. Have a nice day. I hope that was... When I say, see, you all can do this, you already know the answer or how to do this, and then you don't. You're going to have other things to feel anxious about. Let's not make it that. So I want you to do something for me that I think you can do. I have a bar. It is, let's go with 5 meters long and has a mass of 20 kilograms. Okay. If I break off a piece that is, I don't know, 0.6 meters long, how much mass does the piece have? I think you can do this, but I'm curious. I see you all downshifting into your calculators. Good for you, I guess. I'm not sure your calculator is all that necessary because you are smart people, but I'll give it to you for a minute. Try it out. So my understanding is that you've all had chemistry, so I should be able to count on the whole idea of density, which is what we're talking about here. But I'm not, you know, I'm not a fool. How many of you are going to do 20 kilograms is to 5 meters as unknown kilograms is to 0.6 meters? Oh, none of you. How many of you did it this way? How many of you did it another way? Not much more of another way to do it. Is the other way you did it, find the density, set that equal to 20 over 5, and then multiply the 0.6 times the density? Because there are no other alternatives on how to do this. It is a proportionality. In fact, 20 divided by 5 is 4 times 0.6, thinking 2.4 kilograms should be our answer here. Let's just set this aside. This object has a width of 5 meters, a height of 4 meters, and a mass of 60 kilograms. I'm going to cut out a piece that is 1 meter by 1.5 meters. What will be the mass of this piece? This is becoming quite educational for me. If I had known this idea was something you didn't have, I would have always done this a little different. 4.5 kilograms. Now, if you don't know what we're doing here, I will make it clear. We are doing density problems. The same kind of density problems you probably did in chemistry. We're doing them a little different though. In chemistry, you were often given the density of a material and asked maybe how much mass would a certain volume have. That's not different from this. In fact, the example we have over here would be known as linear density. Linear density is something that you would find in things like guitar strings or violin strings. The strings that play the higher notes have a small linear density, and the strings that play the lower notes have a more massive linear density. When you buy the strings, they are sold to you not with their linear density, but they are packaged by the manufacturer in kilograms per meter. That's the way in which you consider linear density. In fact, there's a symbol for linear density. It is the Greek letter lambda for L, linear density. And it's a mass per unit length. Thus, density for something that has linear symmetry is a mass per unit length. Slide over to the second example. This example is about, there's two ways to say this. Surface density is one way to say it, or areal density is another way, as in area density. We use the lowercase Greek letter sigma for S, surface density. It's a mass per unit area. And this particular example was 60 kilograms per 20 meters squared. I broke off a piece that was 1.5 meters squared. I could look at the ratio, or I could have said sigma times 1.5 should give me my mass. In chemistry, you did volumetric density, mass per cubic meter, or mass per liter. One of those two, depending on whether you're dealing with solid objects or probably liquid objects or gases, you dealt with some kind of version of volumetric density. In physics, we generally use the symbol rho for volumetric density. It's not going to come up in here because we're not going to find the moment of inertia of any three-dimensional objects. Mostly because you guys don't have a coordinate system that works. I know that sounds like a weird excuse, but I would need you to know more than just X, Y, and Z. There are other coordinate systems out there, coordinate systems that lend themselves to objects that might have other kinds of symmetry. Like I wouldn't use X, Y, and Z if I wanted to describe a ball. I would use spherical coordinates. And I wouldn't use X, Y, and Z if I wanted to describe something that looked like a can. I would use cylindrical coordinates. X, Y, and Z is only good for things that look like a box. So in math, we have more than one way to describe the location of something. You already know that because you guys have Cartesian and polar coordinates. Those are two different ways of saying the same thing. So we will do two-dimensional problems and we will do one-dimensional problems. So our problem that we have in front of us today is a one